Now we've already talked about one kind of transfer function, h of s. There's another kind of transfer function we'll be using, which is h of omega. And you'll want to know two things. First is how to find it. And the second is what does it mean? So how to find it is scary easy. Find your h of s, and then just let, every time you see an s, change it to j omega. And that's your h of omega. Sometimes you'll even see it written h of j omega, just to emphasize that fact, that it's just h of s with all the s's changed to j omegas. So as a quick example, if your h of s is equal to 2 over s plus 3, your h of omega transfer function would be 2 over j omega plus 3. So now that we've talked about how to find it, let's answer the so what question. Firstly, Jonathan, is the transfer function h of omega, is it going to be real or is it going to be complex? Yeah, for those of you who couldn't hear it, he said complex. So if we want to graph it, it might be natural to want to graph what it looks like. But the problem is we can't really graph it versus say, omega, which is the same thing as 2 pi f. It's hard to graph it versus that because it has both a real and an imaginary component. Or alternatively, we could say it has both a phase, a magnitude, and a phase. So if I was to try to graph this, I'd have to do something like the real part of h of omega on this axis, and then have a z-axis that would be the imaginary part of h of omega, and then I'd end up drawing a surface in three-dimensional space, really hard to draw. So I'm not even going to try. Instead, I'm going to just draw one part of h of omega, which could be the real part, it could be the imaginary part, but it turns out that for electrical engineers, it's far more useful to not split it in rectangular coordinates, real and imaginary, but instead split it into polar coordinates, where it has magnitude and angle. And if I graph h of omega for a particular transfer function, it might look, here's one example of what this graph might look like. And this frequency down here, I would call the cutoff frequency, because this would be the h of omega is a low pass filter. You can kind of see that if you put in low frequencies here, it's going to pass them. And if you put in high frequencies, it's going to block them. This,
Sir, I have a quick question.
Yeah.
Is that negative j omega? Is it positive? Is that a negative sign right there?
It should be positive. Where do you see anything that looks like negative?
At the h of omega.
All the way up here?
No,
Same question. I just assumed it was positive.
Let me, down here. No?
Yes, sir. That's the one.
That's where it was, sir.
Gotcha. Yeah,
Yes,
let me make that clearer. Yeah, that's a positive. So this is, when you hear about a transfer function, this is the intuition. This is what I want you to think of. That if you graph that, the magnitude of that transfer function versus frequency, you can just read out what kind of thing the system does. If it's a low pass filter, if it's a high pass filter, what it does. And in fact, let me give you a better definition of this. H of omega describes what a system does to a sinusoidal steady state input, just like we talked about in EE230. So in other words, if you have a cosine of a particular unchanging frequency, and here's our sinusoidal steady state input, and it's going into our system that has some sort of transfer function, we already know what the output will look like, even before you took this class. And Chow, can you tell me what that is? If you put in a cosine of 3t into any linear time invariant system, in other words, into any circuit that's composed of just capacitors, inductors, resistors, voltage sources, current sources, what will the output of that look like?
3t.
And don't get hung up by the fact that it's 3t. I mean, it could be any frequency, but what will the output, if you put in a cosine, what will the output look like?
Is 3 over...
Well, let's start off with a simpler question. If you put in a cosine, could it possibly look like a square wave out for a particular circuit?
I don't know.
No. Cosines are really unique. If you put in a square wave into a circuit, into a typical circuit, let me graph this over here. If you put in a square wave into a circuit, if it's a low-pass circuit, I think you did this lab, it might look like this coming out. And if you put in a sawtooth wave, you might get something else. Something like that, say, if it's a low pass. And if it was a high pass, you'd get something that looked like that. But sinusoidal steady states are unique in that they will always give you a sinusoidal steady state out. The only difference is that you'll get a change in the amplitude and you'll get a change in the phase. But remember, we did that in circuits too, because let's see, where are you? Chow, just finishing that up. When we did, what kind of analysis method did we do in circuits 2, which used the fact that a sinusoidal steady state input will give you a sinusoidal steady state output, and you only need to know what the amplitude and the phase is. There's a particular analysis method that we used. Do you remember its name?
No, sir.
Anyone want to help him? Preston?
Phasers.
Phasers, yeah, exactly. So we used the phaser method, which said that sinusoidal steady state in gives you a sinusoidal steady state out, and it's completely described by just its amplitude and its phase angle. And of course, you also need to know its frequency. Okay, so because we already know that if you put in a cosine of 3t, you're going to get out a cosine of a 3t. The only thing that could possibly change are two things. And Preston, what are those two things?
Magnitude and angle.
That's it. Angle or phase. Those are the only two things we need to know. Now, here's the crazy thing. You know how to find this guy for a circuit, right? We just went through a test period where you found H of S, replace S with J omega. Now, you want to find out you want to know what this A is and what this theta is. And the crazy thing is that this is your transfer function evaluated at omega equals 3. Because their input frequency is 3, and so we're going to evaluate it at 3. And then this is a complex number. Like Joe said, it has a magnitude, which is this magnitude. It has an angle, which is this angle. That should be crazy to you.